Okay, so we have this population. This is the population we're starting with, okay? It's nice and normally distributed. It won't always be normally distributed, but this is the one we're beginning with. I'm going to take a sample of 5 out of this population, okay? So let's see. I can find my mouse. Okay, so it took 5 out of this, and this is the mean of that 5, like n equals 5 sample. Does that make sense? Okay. So we're going to do that again. Would this take a really long time if I keep just doing samples, one sample at a time of 5? Yes. So, but do you see how varied each sample can be? Along here, the average of that sample, okay? So let's do a whole bunch of them at once. So I'm going to do 10,000. Put them all on there at once. What do you notice that's starting to happen? Yeah, it's becoming, let's do another 10,000. Is it getting closer? Do you see how it's changing a little bit? And another 100,000. Okay, I'm going to try to fit a normal model to this. Does it fit pretty closely? Okay, so your one sample may not meet the mean of this at all, but if you sample all possible groups of 5, your distribution at the end, your sampling distribution ends up being a normal distribution with those attributes. Does that make sense? I'm going to do a lot more with that, but that's I think it's hard for you guys to wrap your head around. Okay, so over and over and over and over and over, I'm taking these samples of the same size. You don't have to do that by hand at any point, don't worry. Okay. So this is just drawn out for you what I was showing you on that little example. Okay. So let's go ahead and turn the page. We're going to figure out how to solve the problem of our sample of plants. So the first thing you have to do is you have to decide if you have quantitative or categorical. You have different formulas based on the type of data that you're looking at. Okay. We can talk about our center here. This is kind of small. What this is saying is the mu of x bar. That's the mu of your sampling distribution. It equals the population mean, so it equals mu. Can you guys see that there? You can see here. That's if we have quantitative data. That's when we talk about x bar, right? Or mu. What do we talk about if we're looking at categorical data? You guys remember? The p's, right? The proportions, okay? So this, again, it's kind of small. Mu of p hat is equal to p. So remember, the p hat and the x bar, those are from your samples, okay? The p and the mu, those are from the population. So we're saying that the mu of your p hat is going to be the same as p of the actual population that you're given, okay? For our standard deviation. So again, I'll just rewrite this because it's kind of small. Sigma of x bar is equal to sigma over square root of n. You guys remember in the first unit when the one formula had the square root of n in the denominator, and we said we didn't really need that right now because our sample size was always 1. Okay, that changes. Now n is going to matter for us. For categorical data, your sigma of p hat is the square root of p times 1 minus p all over n. Okay. We're going to talk about later, if you don't actually know the standard deviation of your population, if you don't know sigma and you only know S, the standard deviation of your sample, you have to do a t distribution, but we're going to get into how that affects the shape of the graph later. Okay. All right, so then when is our sampling distribution normally distributed? So the little animation, when did it become, like when did it start to actually look like a normal graph? Yeah, after you sampled a lot, right? Okay. So that leads us to our central limit theorem. So we're going to squeeze it in here. If your sample size is large enough, and for us that means n is greater than or equal to 30, your sampling distribution will be approximately normally distributed. Regardless of the original, population shape. So your original data, your original population can be completely skewed one direction or another, but if you take samples that are large enough and do a sampling distribution, it will end up being normally distributed, approximately normally distributed. Okay? Nothing is ever perfectly normal. I don't know that I've emphasized that enough with you guys when you're writing that in your answers. Like with the normal probability plot, it's nearly linear or approximately linear, which leads us to think the data is approximately normally distributed. Okay, always include that when you're describing it. I didn't take off on your test for this, but be careful with your wording. Always include approximately or nearly. It's close to that. Okay. All right. So the way we test this to decide if our distribution is going to be normal, if we have quantitative data, your check you have to do every time is n is greater than or equal to 30, or the original population is normally distributed. For categorical, we have our proportion that we have to deal with. So the way you check for that you're going to do n times p, and that has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So you have to show both of those things when you're checking. We're going to start checking conditions in this unit. want to make sure that sample size is large enough. The larger you get, the more closely you will be approaching the true mean. Okay, so you're always trying to find the truth, even though you're sampling. So let's try one so you can see how this works, okay? Because right now you're just writing a lot of formulas, I know. All right, so back to our heights of students here. They tell us the population is normally distributed, mean of 66, standard deviation of 4. Okay, so we know all of that. Is this a sample means or a sample proportions problem? Means, right? Okay, everybody sees that, so it's quantitative. Okay, so label it. Say I'm doing sample and then X bar. That's telling us sample means. Okay. What is my sample size? What's N? 10. Okay. The next thing we're going to do is check our conditions. All right, so to decide if we can use a norm CDF on this, we would need to know the sampling distribution is normally distributed. Is N greater than or equal to 30? No, so that can't be what our check is. What's our other option then? Yeah, is our population normally distributed? Yes, okay, so we can say population is normal, and we know that because it was stated, okay? So that's your first check. And then the other thing you always end up checking is, do we have a random sample? Does it say random sample in this one? It just says sample, right? Okay. So it's not stated that it's a random sample. We're going to assume that it's random. Okay, but you still have to write that down. So random sample. Assumed. All right, so there's your second check. So now we can proceed with actually finding the likelihood of this happening with a sample of 10, okay? So we must make a picture. Our sampling distribution is going to be normally distributed. We've got 66 right in the middle. 72 is somewhere over here, right? And we're looking to shade over there. All right, so a couple things we have to establish here. I don't just want mu, because I'm not talking about the population. I'm talking about the sampling distribution with the sample size of 10. So I want mu of X bar, so like the mean of my sampling distribution. What does that equal? 66. Yeah, it is the mu of the population. Okay, so this is 66. All right, then we have to find sigma of the sampling distribution. We had a formula for this. What was it? Okay, so now over square root of n. Write down the formula. Show me you know that. And then we can plug in our values. What was the standard deviation of the population? 4 over square root of 10. Okay. You can go ahead and key that into your calculator. What if you can't? You guys sharing back there? Sharing is here. All right, I'm just going to jot down 1.26. That's close enough. Okay. So that's the standard deviation of our sampling distribution. That's significantly smaller than the standard deviation of the population, right? Okay. So now let's figure out the likelihood of this. So we're going back to finding a percentage, like finding the area under the curve in that little shaded region. So you're still going to use norm CDF, okay? So norm CDF. I'm going from 72 all the way to the right. And then instead of just mu, I have mu of x bar, so 66, label it mu of x bar. And then instead of standard deviation of the population, I'm using my new standard deviation of the sampling distribution, which is 1.26. So label that sigma of x bar. Okay. And calculate this for me. I'm going to write approximately. What do we get? Yes. Okay. Yes. Yes, because we're not talking about the mu and sigma of the population. We're talking about the mu and sigma of your sampling distribution. Okay. That's why you had to write it in the others, because it does change depending on what we're doing. All right, what do you guys get? What? Is that all it said? Oh, times 10 to the negative. Okay, so what does that really mean? 0.000, like a whole lot of zeros before your 9. So what do you think that means? What? Very low likelihood, like almost a 0% chance? Yeah, so I would say it's approximately 0% of samples with n equal to 10 have a mean, so have x bar over 6 feet. So it's extremely unlikely that you would find a sample of a randomly selected sample of 10 students from the school that have an average height over 6 feet. Okay? Back to this. Let's see, where is it? Not that. That's not what you mean. Back to this. Do you guys see how the sampling distribution is a lot narrower than the original population? Okay, your standard deviation is smaller when you're doing a sampling distribution than it is in the original population. Okay? Seeing it together slowly. All right. There we go. Okay, any questions on that first one? So guys, if you see this on a quiz or test, I want all of these details included, okay? I need you to tell me, hey, I know it's a sample means problem. I need you to check your conditions. You know your sample size, you know your mu of x bar, your sigma of x bar, you've given me a picture. You've shown me what you're doing on your calculator. Like, all of this has to be there. You can't just get to this problem and go, oh, about 0%, and that's your answer. Okay, that's not complete. That doesn't give me everything I need. All right. Let's try again. So let's look at the next one here. According to the census here, I think that's supposed to say like 2000 census, not 200 census. Census from the year 200. Yeah, go ahead. All right, 80% of U.S. citizens have earned a high school diploma. We're going to take a sample of 120 U.S. citizens. So what do you think? Is this proportions or means? Am I looking at a p hat or a p here, or am I looking at a mu and an x bar? Yeah, proportion, 80%, 8 out of 10, that's a proportion, okay? So, tell me, I know this is a sample proportion, or a p hat problem, okay? All right, off to the side here, I'm gonna state some things that I know. What does n equal? $120. Yes, there's 120 people. All right. What about P? 0.8. Okay? That's from the population. 80% have this high school diploma. Okay, so that is my P right there. All right, so we're going to find the mean and standard deviation of our sampling distribution. So what we need to look at are, you can make a sketch for me. Even though we're talking about proportions, the sampling distribution is normally distributed. What goes in the middle? 0.8. Okay. When you do proportions, your mu of p hat, it's equal to p. So in this case, it's equal to 0.8. Your sigma of p hat. We have a formula for that. What's the formula for sigma p hat? Square root of what? P times 1 minus p all over n. So for us, that's going to be 0.8 times 0.2 all over 120. In the back there, 0.0365. Yeah. I'm okay with that. Okay, I did all of that, assuming that this is normally distributed. Do I know that? Should I have checked something first? Yes, okay, so that's what we're going to do in part B. Really, I should have done B before A. So what's the shape of our sampling distribution? Normal, how do we know? So let's talk about our checks here, our condition checks. Check conditions. The way you check for normality with a proportion is you have to do n times p. Remember, we're looking to see if that's greater than or equal to 10, and n times 1 minus p. Is that greater than or equal to 10? Okay. So for our problem here, what's my n? Okay, so 120 times 0.8. What does that equal? 96. Is that greater than or equal to 10? Yes. Okay, off to a good start. Then I have to do 120 times 0.2. What does that equal? 24. That is greater than or equal to 10. So, check. We know that it's going to be normally distributed, approximately normally distributed. So we would say the shape of the sampling distribution will be approximately normal. Or approximately normally distributed. And how we know is the checking our conditions there for normality. What's the other condition we're supposed to check? Is it a random sample? What do you think? Is this a random sample? Does it say that it's random? Just a sample, so what are we going to say? Assume. Okay, because it has to be random, but you still need to state it. So, random sample assumed. All right, we're okay with parts A and B. right, part C. Suppose the sample was 30 Americans instead of 120. Would the center shape or spread of our sampling distribution change, and why? Okay, I want you guys to think about this. Something's definitely going to change. Maybe a couple of things. So I'll give you a few minutes here to think about this. Talk to each other about it. Jot down what you think. I'm just going to take attendance while you guys are talking. All right, so center, what do you think, guys? Mu of p hat, is it going to change? Nope, it's still 0.8, okay? That is not affected by the sample size. What about sigma p hat? Yeah, that's going to be different, right? So it's going to be 0.8 times 0.2 over 30 this time instead of over 120. So what is my new sigma of p hat? Did you guys talk about that to each other? Does that make sense to you why that one's going to change? I'm changing one of the values in the formula. Sample size definitely impacts the standard deviation of your sampling distribution. Okay, so center, no. Spread, yes. What about the shape? Yes, I hear a yes. Why do you say yes? Yeah, it doesn't work when you do the n times p, n times 1 minus p, right? So your check here, when you check this condition, if you do 30 times 0.8, all right, that's 24, that's still bigger than 10. But 30 times 0.2 is only 6. That is not greater than or equal to 10, so not met, okay? So you don't know that it's normally distributed anymore. Your sample size is too small to guarantee that. Okay, yes?
So if you know it's not normally distributed, then like...
You can't do like the norm CDFs because that's based on a normal distribution.
Would the mean still like work? Like
The mean is still going to be like, that's still the mean, but the shape of it, like,
okay.
I don't know, could be skewed one way, could be uniform, it's not going to be normally distributed. Which it makes sense, guys, right? To use norm CDF has to be normal, right? Okay, so remind yourself of that. All right. So let's do the next part. What's the probability that in a sample of 120 U.S. citizens, we're going back to the sample size of 120, that over 90% have a diploma? Okay, so conditions, we checked those up above, right? So check above. We were good with our conditions, right? All right, so let's make a picture. In the middle, I've got 0.8 for the 80%. And we want to know what's the probability that over 90% have a diploma. So 90% is somewhere over here. Over 90 is there and above, right? Okay. tell me things that you know. What is mu of p hat? 0.8. We found sigma of p hat up above, right? Didn't we already do that in the first step? Yeah, everybody with me there? Okay, we don't need to do it again. 0.0365. You can also tell me you know your sample size. It's 120. Okay. What do I do with this information to actually find that probability, the area of the shaded part? Norm CDF. Good. All right. So I'm starting at 0.9. Now, technically, you can go all the way to infinity, but where is this going to end if we're talking about? Yeah, so you could just go to 1 also, and that would make sense to me. So from 0.9 to 1. 0.8 was our mu of p hat. 0.0365. That is my sigma of p hat. All right, what do we get? Approximately, what do we get? All right, are you getting like 0.003? Around there? Okay, so what is that in percents? Yeah, that's less than 1%, right? Okay, it's 0.3%. Gotta pay attention to our decimals. So I would say there is about a 0.3% chance that a sample of 120 U.S. citizens will have 90% or more with a diploma. Because we're not just saying there's a 0.3% chance that one U.S. citizen has the diploma. It's of this sample of 120 that 90% of those people would have the diploma. Okay? Yeah. All right. So you guys try. I don't know why it goes A, B, C, D, C, but try C that's after D. Okay? Work on this one for me. So your sample size has changed. Yes, it's a very similar idea, but it's really interesting because you're gonna have to go through this and then when you think about your picture, we need to figure out what this means in percentage. Well, yeah, you gotta do this stuff first. Okay? But then you are going back to that price for Are we doing okay with turning 150 into a proportion? Yes, you recognize it. That's why we do Well, so if it's 0.038, that's if there's another zero, That makes it a little more. That's good. If I question you recognize Does that make sense? You're going like you're reading it from like
I don't think that's right.
So like okay, good. We'll go right after lunch, okay? Okay. So I'm going to make a sketch. 0.8 is in there. What am I talking about with this 150? Because I can't put 150 on this. Yeah, out of 200, so that's 0.75, right? Which is somewhere over here. And I want to know less than that, so that would be this side, right? Okay, so you're going to use your calculator. Norm CDF. 0 or negative infinity, it really doesn't matter. 0.75, 0.8, 0.028, and this was mu of p hat. Okay with that. And you get approximately 3.7%. So what does that mean? Like, what's the contextual answer to this? Troubles? Mark, you got a question?
Yeah. How do you get 0.75?
The 0.75. So this, because it says we're looking for the probability that less than 150 out of 200. That's not a proportion yet. I need to make it 1, and then that's the value that I'm looking at. Okay. All right. So what does this mean contextually? What would you tell me?
There's about 3.7% chance. You got from a sample of 200 US citizens, less than 150.
Perfect. Yes, that's exactly right. Okay. Did you guys hear him? Okay. Does that make sense how you rate those conclusions? Okay, number 2 here. I want you to do A and B, and then we'll go through them together. So the first one is looking at one randomly selected apple, okay? And part B is talking about a sample of 3 apples having the average, okay? So see if you can approach those slightly differently. We'll give you some time. This is the last one we're going to do in our notes today, okay? Talk to each other as you're working on it, guys.
Yeah, so the check is complete. It says complete.
All right, guys, what's playing test grades while you're working? Oh, Yeah, this is the percentage.
Yeah, it's just the sample size that is changed. So N is changing. So the standard deviation.
Standing deviation.
Very good.
Is there a way to draw the
Sort of being for that, you just have a different.
The picture is the same.
We get these to get their scores. Yeah, I'll be like,
I knew this was gonna happen. Matt.
He jinxed himself. He jinxed himself.
I was thinking if you got it, you can't feel the confidence.
It's like,
yeah.
I feel like it's stated that it's normally distributed.
If you're checking your. Like population. And don't forget to check your conditions on these. Yeah, that's just.
Oh yeah, oh yeah. Actually, when I was there, it was crazy, but I was
Yeah.
Worrying a lot.
I was like,
I don't know, it was like having like, and I thought it was supposed to work.
So how are you?
Stop finding those classes are like 5 years. They're 5 years. End of their life.
Like, no pictures.
I was gonna drop that because I remember like very black and white. And then I was like, but I don't know what those 2 and 3 are. Like, it was why. Yeah, I was just like, I didn't have money for like the entire like day. Yeah. And then she was like, just and I did.
So clearly it was.
It matters. It really has.
Yeah. Come and it, I don't know where you're There you go. Like write out everything, all of those little details. For sure, one more.
Thanks, Kelly.
We have just like Columbus Day. But I guess it's because of the classes that like because of her birthdays that it's like a whole week that
I actually just said that today. Yeah.
yeah, I feel like she's really was born.
Yeah, I was like,
This guy was happening in one day.
The quiz?
Okay. Lots of different answers to the first one. Let's see what it is.
It's like the one that you have like a random. What is
Oh, really? Oh, I thought it would be.
Writing that.
It's like bigger.
State that it's randomly selected teachers.
I know you're gonna write one or the other.
Better not random.
So I'm not gonna give you the rules that aren't random.
I don't have a I only know the last. Wait, actually, I think I did that with the